Hey kiddos, let's just pretend like I said a stupid YouTube intro and move on. Today we're talking about an extension of the binomial theorem that we did not talk about last year, and this extends to when you're dealing with a binomial in this form of 1 plus x to a power where that power can be negative or a rational power. So if you notice, the formula that's stated. Now, if we were in person, I could go through kind of where this comes from, but on a YouTube video where I have limited time, that's not going to happen. So, if you notice, it creates what is called a power series, which is an infinite polynomial. And this power series has a pattern where if you notice, the powers of x increase like this, and then the coefficients become, they change with each individual term. But once you practice it, it's really not that bad. So the first term is just 1, then it's n times x, and then it's this thing that kind of looks like combinations. Well, I mean, it is combinations, where it's n times n minus 1 over 2 factorial, then x squared, and then we just continue the pattern. Now this happens infinitely. But most of the time the problems are just going to say, like, do up to this term, and we just kind of go from there. Okay, so we're going to do just 3 example problems together. You'll realize it's not too bad. It's a little obscure, and this formula, sadly, is not on the formula sheet. So you kind of have to realize, you kind of have to really get comfortable with the pattern. But yeah, okay, let's do it. Okay, so we have this problem. Oh, crap. One thing I meant to say. This does not work if x is anything but in between -1 and 1, because otherwise you would just be infinity. It doesn't work. It would diverge, but that's more of a Cal 2 conversation that we'll talk about later. So it's always accompanied by some type of, statement. Like on this one, it says absolute value of x has to be less than 1/2, because that would make this term more than 1, like the formula. But anyway, moving on. So we are often going to kind of rewrite it. So on this one we have 1 plus 2x to the 1/2. So our n from the formula is 1/2. So if we expand this out, we're going to the x cubed term. We would start with just 1. And then plus 1/2 times our x term, and then plus 1/2 times our power minus 1, so -1/2 over 2 factorial times, times 2x squared, and then one more because we're going to x cubed, so plus 1/2, -1/2, -3/2 over 3 factorial 2x cubed. And then all we have left to do is just multiply all this junk out. So that would give us 1 plus x. So let's see, what is this? So we have, this would be -1/4 divided by 2 is -1/8, but then times 4, so minus 1/2 x squared. Let's do that again. We have, this would be positive 3/8 times 8, though, is going to give us just positive 3. And then 3 divided by 6 gives us positive 1/2 x cubed. So yeah, so let's make sure we understand that. This would be our answer. So this is the expansion of this up to the x cubed term. Make sure you understand that this, I really shouldn't put equals. I should be a better mathematician than that. I should put approximate, because in reality, this is actually equal to this polynomial, but with an infinite terms. So this power series would keep going if we wanted it exactly, but this is this expansion is approximately our answer here up to the x cubed term. So it's pretty straightforward once you get it. So you just, your x term, increases powers, and then the coefficient is just this like combination pattern that you'll get used to. So let's do another one. So on this one, I'm going to rewrite this as 2 times 1 minus 3x to the negative first. So I'm just going to ignore the 2 for now, leave it out front, and then expand the 1 minus 3x to the negative 1 using the formula that we stated. So we would start, we get just first term is 1, and then it is plus our power negative 1 times negative 3x. And then we continue. So plus negative 1, negative 1 minus 1 would be negative 2, all over 2 factorial, and then negative 3x squared, and then one more term, negative 1, negative 2, negative 3, 3 factorial. Ooh, I've run out of room. Negative 3x cubed. So, then we expand that big ugly guy. I mean, shouldn't say expand. We're going to just simplify this big ugly guy. So, like, remember, technically, that has an infinite number of terms, but we only care up to the x cubed term for this problem. So, that gives us 2 times 1 plus 3x. That all cancels, giving us 9x squared. And then the last term, this would simplify down to negative 1. And then times this cubed would be positive 27x cubed. Then all we have left to do is distribute the 2. So I'm going to stop at the x cubed term, so just 2 plus 6x plus 18x squared plus 54x cubed. And that's our answer. All right, one more and we'll be on our way. So this one's going to be a little more complicated. So we have this term, the square root of 1 plus x over 1 minus x. So just like all the other examples, our first step is going to be to rewrite this. So I can rewrite this as 1 plus x to the positive 1/2 times 1 minus x to the negative 1/2. So what we're going to do on this problem is we're going to expand each of these individually first. So let's do that. So 1 plus x to the 1/2. Using the same practice we've done this whole time, expanded out would start with just 1 plus the power times the x term plus the power 1 minus the power over 2 factorial x squared. So if we simplify that, if we simplify that, that is 1 plus 1/2 x. And then what would that be? Minus 1/8 x cubed. No, sorry. Not cubed, squared. Come on. There we go. So let's do the next term now. So 1 minus x to the negative 1/2 would be 1 minus the power times the x term, which in this case is negative x. Then power is negative 1. 1 minus the power is, negative 1/2. 1 minus the power is negative 3/2. Oh my god, Ben. All over 2 factorial x squared. Dot, dot, dot. So that is equal to 1 plus 1/2 x, and then plus 3/8 x squared. Okay, that took a while, but let's make sure we understand what happened. We rewrote this to look like this. We have 1 plus x to the 1/2, and then 1 minus x to the negative 1/2. Then we expanded each of those individually. So we're like halfway through this with this problem now. So what we're going to do is, since I want the total expansion of this, what I'm going to do is now rewrite this. So let's just use red. So this turns into 1 plus 1/2 x minus 1/8 x squared, technically dot dot dot, times 1 plus 1/2 x plus 3/8 x squared, dot dot dot. Alright, so we're almost there now. We want this total expansion. So remember, this is this now. So we want up to the x squared term. So we're just using distribution. We're distributing this infinite power series with this one. We only care about up to the x squared term. So let's just start with 1. So if we distribute 1 into this power series, we're going to get 1 plus 1/2 x plus 3/8 x squared. Anything after this term, when you distribute 1, is going to be a power greater than x squared. So let's move on to this. So let's distribute this 1/2 x into this, only caring about terms up to x squared. So if you distribute 1/2 x, first term is going to just be 1/2 x, because 1/2 x times 1. Then the next term is going to be 1/2 x times this 1/2 x, so plus 1/4 x squared. And if we went any further, 1/2 x times this term would give us x cubed, so I don't really care. So last step is to distribute this guy into here, and I can only distribute up to 1 if I'm only caring about x squared. So that's minus 1/8 x squared. Now all that's left is to combine like terms. So let's do a different color. We have 1, and then let's see, x to the first is just 1/2 x, 1/2 x, so plus x. And then all the x squared. So we have 3/8, 2/8, so 5/8, and then minus 1/8, so 4/8, so positive 1/2 x squared. And that's it. So I wish I was teaching this in person. I know it's probably not going to translate as well on this video, but when we do eventually get to this in class, we'll probably spend a large portion practicing. Once you do it yourself a few times, you get the hang of it, and it's really not that bad. I know it probably looks intimidating. All right, talk to y'all later. Love you. Bye.